Alright, so for this is the last video on incompressible elasticity. One of the things with the Lagrange multiplier method is that it turns the minimization problem into a saddle point problem. So you want, if you recall let me just sketch back to this example that I had that is to visualize sort of what you are solving. The standard elasticity problem for hyperelasticity is the minimization of the total potential energy, and that total potential energy is convex. And so you basically go through some sort of descent method and you get the optimal solution. When you add a constraint, then the problem is to finding the minimum along some constraint hypersurface, like I showed here, solving the minimization of that function f that I defined, but now subject to be on this line. How do you find that? You can turn this constraint minimization problem into an unconstrained minimization, well, unconstrained optimization problem by adding this Lagrange multiplier. So that's what I was explaining in the first video, where you add the Lagrange multiplier. Now that problem is actually not necessarily a minimization. It's a saddle point problem, which means you want to find a point for which the derivatives are zero, but it's going to be a minimum of f, but not necessarily a minimum for the Lagrange multiplier. And so when you have this type of saddle point problem, you might not have a stable system. So you might have oscillations in your numerical solution, and there's a condition for how to check that that is not the case. So the mixed formulations, so formations that have some minimization of some energy with some constraint, can be broadly described for the linear case at least, in this type of description, where you have two equations. This is sort of the residual for the displacements, and this is the residual for the pressure. So you get two equations where you are solving for the displacements. So this has to be satisfied for all variations of the displacements, and this equation has to be satisfied for all variations of the pressure. So that's how we got our two residuals. And the form of the first one is the A term. That's basically the equivalent of this sigma delta D. And then the B term is a term that has the Lagrange multiplier with some condition on the variation, typically the divergence of the variation. And then the residual for the pressure is basically just your constraint. So B is the constraint. B hat is the constraint. So it's not this one, sorry. It's like this, but with dp divergence of u. So actually that's this b q of u. So it's the same form as this one. So you're constrained, but now the variation on the p with the actual displacements. So that's for the linear case. It looks like this. And so for the linear case, you can prove that in order for this system to lead to a stable solution, basically that the off-diagonal components are non-singular, you need some condition on these spaces. And yeah, so at the end, what you need to show is that this constraint, the norm of this constraint relative to the norms of these two spaces has to be greater than some constant beta. This is named the BB condition for the people that came up with this condition, that has to be satisfied in order for the system to be stable. And this is kind of related to, let me come back to the initial Lagrange multiplier equation. Remember that when in the first video so long ago, I had this the functional with the additional constraint with the Lagrange multiplier. This off diagonal terms, that's basically what you get from this B term that I have below. This B, P eta and B Q U. Those basically give you these two terms. And so depending on whether or not these matrix have full rank or not, you might get oscillations in your solution. So these will lead to basically these are called checkerboard patterns. I should add a slide on this, but the pressure field doesn't look smooth, doesn't look like this, but it looks like it looks a little bit jagged. It has like high pressure next to low pressures, so it looks like a checkerboard. And that's related to sort of the rank of this B right here. And at the end of the day, this BB condition that I have here that you can find on the book, this one is related to, so this basically is connected to that B matrix once you discretize. Yeah, so based on this, it is stable or not. I'm not gonna go into more details for this. All I want you to know is that there is some special condition for this type of problems, which are called mixed problems, where you have displacements and another field because you have a constraint. So that's what I want you to know. This, can you evaluate this? Yes, actually you can evaluate this for linear problems, and for some discretizations you can actually try to figure out what these norms are and check whether or not you will satisfy these conditions for some constant B. But in general cases you might not be able to do it analytically. And so the way you can check this condition is with a patch test. Yes, so for simple cases, so for simple elements, for linear elastic materials, you can derive the actual im sup of this term right here and check whether or not that condition is satisfied. In general cases, you cannot, and so what you can do is a patch test, which is a small mesh like the ones that we have been using in this class. So a small mesh where you have maybe 5 elements and you prescribe some displacement at the boundaries, and based on that you try to solve for the interior nodes values and the pressure values, and you can see in this small problem you can evaluate these norms and check whether or not this condition is satisfied. So that's typically what is done. Now, for nonlinear problems, even if you satisfy this BB condition, you're not guaranteed to have a stable solution. And that is because this condition is, the way it is derived is because of the linearity of this A term. This bilinear form is bilinear. And so the condition is based on some assumptions on this linear operator. But in the nonlinear case, even if you satisfy this condition, which is based on the constraint B, you might still not have a stable discretization if the A is nonlinear. But at the very least, you should check it, because for the linear case, you do need this condition. And if you want to read some more, you can check the book by Bretzi and 14 on this. Very, very nice book, actually. And yes, an additional thing is there are other mixed formulations besides the one presented here. So the ones that I have talked about are adding just the Lagrange multiplier, that was the first one. Adding a Lagrange multiplier with some perturbation so that you avoid this zero matrix on the tangent. The other one is the Hu-Ashitsu principle, where you add 3 variables. You have the displacements, you have the pressure, which is the Lagrange multiplier, but now you also have an fictitious volumetric strain, theta, and the constraint is that the J, the volumetric change from the displacements, is equal to the theta. And then similar to that last one, to the Hu-Ashitsu variational principle, you can think of adding other strain fields or stress fields and add constraints such that by imposing the constraints, you make these additional variables to be equal to your strains given by your displacements. So, for example, these methods are called enhanced assumed strains, where you have your standard degrees of freedom for the displacements, and then you also have degrees of freedom for other strains. So other strains you can do as degrees of freedom. Well, actually, these are just displacements, and then I should say some strains as degrees of freedom. And then you can guess what is the constraint. The constraint is that the gradient of this displacement is actually the same as this strain. So the constraint is basically gradient of displacements equals f. So this is a very general case where the full deformation gradient is assumed as a degree of freedom. In most enhanced assumed strain elements, actually only some strains are added as degrees of freedom. So it's somewhere in between this and the Huwa-Shitsu variational principle. So in the Huwa-Shitsu principle, the only one you can think of, these were the original displacements. This was this additional strain. So independent variable for the volumetric strain. Independent variable for volumetric strain. And this is Lagrange multiplier. Right, so here we added one additional strain, which was this volumetric strain J bar. And then the Lagrange multiplier is basically to impose the constraint that the J from the displacements equals this J bar variable. And so if you think of an extension of this is what other strains can you add as independent variables, and the one right here is sort of the extreme. This one is extreme, so typically you don't have this one. This will be an extreme where the entire deformation gradient is assumed as a degree of freedom. And so you have your displacements as unknowns, you have the entire deformation gradient as unknowns, and then you need to impose the constraint that the gradient of the displacements is the same as your independently discretized deformation gradient. And that is enforced by a Lagrange multiplier. So P, which is actually the Piola-Kirchhoff stress, is a Lagrange multiplier to enforce. So this is a Lagrange multiplier to enforce that constraint, which is that the gradient of the displacements is the same as your independently discretized deformation gradient, right? So you can see that it's very general, this idea of adding strains. And this is the extreme. As I said, in this case, we are completely independently discretizing the displacement and the deformation gradient. But then you have to make the match, so that's why there's a constraint for that, and that is enforced by some Lagrange multiplier, which is actually the interpretation of the Lagrange multiplier is the Piola-Kirchhoff stress. So that's it. That would be the most generalization of this Huwa-Shitsu principle. In reality, the strains that you add as degrees of freedom are not all the strains. So this is used for things like shells or structural elements where you just want to increase bending performance. So you don't have a full deformation gradient, you have something more like your displacements. So you can think of this as phi or u. And then some strains, not all the strains, some strains. For example, like some bending strains. And then some Lagrange multiplier for those strains. And then your total potential energy is the same. So you have a total potential energy based on your strains given by the displacements plus the strains given by these additional variables, with some constraints such that the some of the strains from the displacements are equal to these additional strains. So hopefully that sort of makes sense. And that just adds flexibility. So the reason why you would add this again is because of this same idea of being too restrictive with your discretization. So you want to add more degrees of freedom so that you can capture a richer set of deformations. So for thin elements, typically the problem that they have is they don't do very well in bending. And so in order to improve that, then you add degrees of freedom for the bending strains, and then that just gives you more flexibility to capture these different bending deformations. So that's the most common application of this enhanced assumed strain. And again, this is sort of a generalization of this Huwa-Shitsu principle to other strains. In the extreme case, you would have the entire deformation gradient as a degree of freedom. But yeah, you wouldn't find this one really. This is like too much. You wouldn't find this one. You don't need that. But just some strains. And going to the idea of reduced integration and stabilization, like I mentioned before, is when you have two ways of adding flexibility to your discretization. You either add degrees of freedom, or you underintegrate your equations, which means that you don't impose them as strictly. Now the problem with reducing integration is that yes, you do reduce the stiffness of your discretization, so you have more flexibility to capture the deformation, but you might reduce stiffness sort of blindly, and that leads to the zero energy modes that you have probably seen in some linear finite element courses. So these are types of deformations that carry no energy, and therefore what can happen is that when you do a simulation, you have this type of hourglass behavior. These are called hourglass modes. And you can find this because, like I said, these deformations do not carry any energy when you don't integrate completely. So if you do like a single integration point for this type of elements, then yes, you are adding less constraints, so your system is not as over constrained, but actually you do the opposite. So you have too much freedom such that there are some deformations that are not plausible, but that you are not having stiffness for. So you have that's why they are called zero energy modes. So the correct deformation would be something like on the left, but what you get is something on the right. So what do you have to do then is, okay, let me do reduced integration, but add back some stiffness to prevent this type of unrealistic behavior. So you can check out the book for a little bit more details, but basically the idea would be that you want to approximate a stabilized tangent by doing the reduced integration, so evaluate say at a single integration point, but add back some stiffness in the correct directions. So the initial stiffness was this integration with the 4 or 8 integration points, which completely enforces your constraints and your weak form. But like I said, maybe too stiff, so why don't instead I under integrate? So if I only integrate a single point, then I have more flexibility, but too much. So let me add back some stiffness, but selectively. So I adjust stiffness in order to prevent these hourglass modes. And so this is, you can look a little bit more on the derivation in the book, but basically you add stiffness along some vectors. These are like rank 1 matrices, which are related precisely to this incompatible, not incompatible, to this zero energy modes. So these vector gamma are related to the eigenmodes of the element, these zero energy modes that you get when you do this reduced integration. So that's a way to stabilize. And again, the advantage of doing reduced integration as opposed to mixed methods is that you don't add additional degrees of freedom, so you still have just a displacement-based discretization. But the disadvantage, like I said, was the zero energy modes because you reduce too much stiffness. So the solution is to add back some stiffness, but selectively. So that's it. That's what I have for incompressible elasticity. And